Hello there and welcome to sections 12.5 and 12.6 on vector functions. In this intro video we're just going to jump into the first two questions on the worksheet. And so let's look at number 1 to begin. So it says to sketch a graph of the following vector functions. Okay, so part A, we have r of t, where r of t here, given that there's an arrow over the r, is a vector quantity. Okay, and you can see in component form, the I and the j components are dependent on a parameter, right? Parameter t. Okay, so just as we did with parametric equations, to just start out to get a feel for what this thing is really doing, let's just build a table. Okay, so I'm going to, in this first column, just choose a few different values of t, and then in the second column, it's going to plug those values in for t, and notice for each value of t, the output here is a vector. Okay, so I want to think about r of t as describing the position of some moving particle throughout the xy plane. Okay, so when t is -1, the output vector is -6, 1, which you see right here in red, and I denote this as r of -1. You want to think about this vector, -6, 1, as the position of the object when t is -1. And then when t is 0, the output vector is -4, 2, and that's right here, r of 0. So there's the position now. Okay, then r of 1, that's -2, 3, then 0, 4, 2, 5, and so on. Okay, so as we let parameter t increase, okay, the position of our object moving in the xy plane appears to be moving along a straight line path. Okay, and if I connect the heads of all of the position vectors, I do in fact get a straight line. Okay, now this really does feel like what we did with parametric equations, and in fact this really is exactly the same thing as what we did with parametric equations. So another way to look at this problem, right, is to say, well, look, the I component of this vector r of t, right, is 2t minus 4. This is really just describing the x coordinate of the head of our position vector, right? If we're placing the tails of our position vectors at the origin, right? The tip is such that the components here are really just describing the coordinates of the location of our object. So x is 2t minus 4, and y likewise is t plus 2. These are parametric equations that describe this line here. Okay, and you can see I've indicated with these purple arrows, right, the direction of increasing t. Okay, so from this example, we're seeing, well, for this vector function, what I'm calling r of t, there's really a parametric description going on here, right? We're just sort of taking a slight shift in perspective, thinking about now our position as described by a position vector as opposed to just a location in the xy plane. All right, so now let's look at the next one, 1b. r of t is cosine t, sine t. So just as we did in the first example, right, construct a table. Here I'm just plugging in multiples of pi over 4 for t, and then here's the corresponding output vectors, which I've plotted in the xy plane. So r of 0, that's the vector 1, 0, right? So that's right here. And then r of pi over 4, that's root 2 over 2, root 2 over 2. And then it goes to 0, 1, negative root 2 over 2, root 2 over 2, so on and so forth. Okay, so here, tracking the heads of our position vectors, well, we're tracing out what appears to be the unit circle. And in fact, this is the unit circle. And just as we did in the first example, right, I can treat this vector function as parametric equations for a curve in the plane. In this case, x is cosine t and y is sine t. And as we know from chapter 11, right, these are parametric equations for the unit circle, right? And it's parameterizing the circle in such a way that when t is 0, we're located at the point 1, 0, and we're moving in a counterclockwise fashion. We complete one trip around the circle in 2 pi units. Okay, very good. So now let's do the last one here in question 1. This is 1c. Notice r of t now is a vector in R3, right? There's an I, j, and a k component. And the I and the j components, they're the same as the I and j components from part B. But now with this introduction of a k component, what's going to happen when we look at, right, the position vectors in R3? Well, I built the table here. And just noting that the I and the j components, they're just the same as they were in part B. You can see, ignoring the k component for the moment, okay, these are just describing those same position vectors along the unit circle in the xy plane. Okay, but now with this k component, right, z is going up, right? So 0, pi over 4, pi over 2, 3 pi over 4, so on and so forth. So let's go ahead and plot some of these vectors. So r of 0, that's 1, 0, 0. That's right here along the positive x-axis. That's just really the vector I. And then at pi over 2, notice I'm not plotting all of these vectors from the table just because it makes the figure here a little too cluttered. But at pi over 2, right, the output vector is 0, 1, pi over 2. So that's right here, right? And we have now a positive k component. And so this is really the vector j plus pi over 2k. So it points upwards like this. And then at pi, okay, we're pointing in this direction, right? Negative 1, comma 0, comma pi. So the k component's a little bit larger. And then we go to at 3 pi over 2, 0, negative 1, 3 pi over 2. So that's over here. And then finally at 2 pi, we're at 1, 0, 2 pi. So if we ignore the k component, right, the I and the j components, they're just running around the unit circle, just like we saw in part B. So another way to say that is that if you were to project the corresponding curve for r of t onto the xy plane, right, we're just going to see circular motion, right, moving around the unit circle. The k component, though, what that's going to do is just going to move us vertically up as we circle around parallel to the xy plane. So if you put those two things together, you get this, what looks like a stretched out slinky, okay? This is what's referred to as a circular helix, okay? So here's the first couple position vectors, right? Their heads are tracing out this green curve, and it's just going to continue along in that fashion, okay? So parametric equations, well, x is cosine t, y is sine t, and now z is t, right? These are the corresponding parametric equations for this helix. And notice I've drawn in this cylinder. Okay, what am I describing there? Well, notice that if you look at x squared plus y squared, you get cosine squared t plus sine squared of t, which is just 1 from the Pythagorean identity. What does that really tell us? Well, here it's telling us that this curve, described by the vector function r of t, lies on the circular cylinder. X squared plus y squared is equal to 1, right? So as t increases, green here is crawling up this blue circular cylinder whose equation is x squared plus y squared is equal to 1. Okay, very good. So now let's look at the second question on the worksheet. This is a little more general. It just says, consider the vector function r of t, which has for its components f of t, g of t, h of t. Identify the domain, in other words, the inputs for the function, and the range, or in other words, the outputs of the function. Describe the graph of r. Okay, so as we saw in these examples from question 1, right, the domain here, the inputs to a vector function are just real numbers, right? So t is going to be a real number. And then when you input a real number into R, the output is going to be a vector in R3, right? Or at least that's what we saw in 1 part C. For A and B, well, there's no K component, so you could just as well say R of T is a vector in R2. Okay, but in this picture I'm drawing, we're thinking about a space curve now. Okay, so as T increases, so from T1 to T2 to T3 on the T axis, okay, the outputs here are position vectors. So there's R of T1, there's R of T2, r of t3. And if we place the tails of these position vectors at the origin, their tips are just describing the location of this object moving, in this case, throughout three-dimensional space. Okay, and just as we saw in the first question, okay, a vector function can be thought of as a parametric description of the moving object, right? And that's where you're just looking at the component functions here, f, g, and h, right, as the respective coordinate functions for x, y, and z. Okay, so if we're moving from left to right here on the number line, right, we're just tracing out this curve you see here. Okay, great. Well, that's going to do it for this intro video. We'll look at some more examples coming up. Thanks so much.